Hello students, myself Ms.Sonali Patil, Assistant Professor, Department of Mathematics, Kokla College, Kolhapur. Today we will discuss normal subgroup and its property from Algebra second paper number 8 from B.Sc. second year. Let's start with the group. See here introduction. Let G be an abelian group under the binary composition multiplication. Let H be any subgroup of G if X is any element of G. Then Hx is the right coset of H in G and Xh is the left coset of H in G. Also G is abelian and hence we must have Hx is equal to Xh for all x belongs to G. If G is not abelian, yet G possesses a subgroup H such that Hx is equal to Xh for x belongs to G. Such subgroup of a group G are known as normal subgroup. The role of normal subgroup in a group theory is a viral importance. Okay, so see here normal subgroup. Definition of normal subgroup: a subgroup H of a group G is said to be a normal subgroup of G if for all G belongs to G and for all H belongs to H, G inverse belongs to H, and this is called normal subgroup. Now see a remark. First remark, from this definition we can conclude that H is a normal subgroup of G if and only if G inverse is a subset of H for all G belongs to G. And second, a normal subgroup is also called invariant or self-conjugate subgroup. And third one, every group G possesses at least two normal subgroups, namely G itself and singleton E, where E is the identity element of G. These are called trivial or improper normal subgroup of G. Okay, now see your examples. So first example, if G is a quaternion group and H is equal to set of 1 minus 1 is subgroup of G, then clearly H is a normal subgroup of G. Okay, now see here one definition of simple group. A group having no proper normal subgroups is called a simple group. Okay, now see one theorem. A subgroup H of a group G is a normal if and only if G inverse is equal to H for all G belongs to G. Okay, so let's start with the proof. Firstly, we can write this given thing. Let H be a normal subgroup of G. Then from remark first, G inverse is a subset of H for all G belongs to G, and also G belongs to G. So this implies that G inverse is also belongs to G. Therefore, from 1, G inverse of inverse is a subset of H. So this implies that G inverse Hg is a subset of H for all G belongs to G. So this implies that now see here we apply left hand side by G and right hand side by G inverse. Okay, so what will we get? G of G inverse Hg. G inverse is subset of G inverse for all G belongs to G. So this implies that H is a subset of G inverse for all G belongs to G, and this gives equation number 2. Hence from 1 and 2 we conclude that G inverse is equal to H for all G belongs to G. Conversely, let G inverse is equal to H for all G belongs to G, then clearly G inverse is a subset of H for all G belongs to G, and hence H is a normal subgroup. Okay, now see here second theorem. A subgroup H of a group G is a normal if and only if every right coset of H in G is a left coset of H in G. Okay, so let's start with the proof. Let H be a normal subgroup of G. Then by theorem first, G inverse is equal to H for all G belongs to G. So this implies that G inverse of G is equal to Hg. So this implies that now here we apply associative property. So we get G inverse G is equal to Hg. Now here we apply inverse property. So this implies that Gh into E is equal to Hg. Now by applying identity property, we get this implies that Gh is equal to Hg. Hence every right coset of H in G is a left coset of H in G. Now here conversely, suppose that every right coset of H in G is a left coset of H in G, Then for any G belongs to G, GH is equal to HG. So this implies that GH G inverse is equal to HG G inverse. So this implies that GH G inverse is equal to HG G inverse. Now this implies that GH G inverse is equal to HE. So this implies that GH G inverse is equal to H. Hence H is a normal subgroup of G. Okay. Now see here one corollary. First one, every subgroup of an abelian group is a normal subgroup. So let's start with the proof. Let G be an abelian group and H be a subgroup of G. Then for any G belongs to G and H belongs to H, we have GH G inverse is equal to GH G inverse by using associative property. This is equal to G of G inverse H. Since G is abelian, so H G inverse is equal to G inverse H. Now here by using abelian property, or we can say commutative property, is equal to, now by using associative property we get GG inverse of H, and now by using inverse property, GG inverse means identity element, so EHL identity element, and now by here using identity property we get H belongs to H. Thus GH G inverse is equal to H belongs to H for all G belongs to G and H belongs to H. Hence H is a normal subgroup of G. Now third theorem, a subgroup H of a group G is a normal in G if and only if the product of any two right or left coset H in G is again a right or left coset of H in G. Okay. Now let's start with the proof. Suppose H is a normal subgroup of G. For any AB belongs to G, consider HA is equal to HB. Consider HA and HB be two right cosets of H in G. Then HA into HB is equal to H of A HB by using associative property. Now this is equal to, again by using associative property we can write H of AHB. Now again by using theorem second, AH means what? HA. So here we can put AH is by HA. So we get H of HAB. Now again by using associative property, HH of AB. Now this is equal to HH means capital H. So HAB. Now AB belongs to G. This implies that AB belongs to G. This implies that HAB is a right coset of H in G. This shows that HAHB is a right coset of H in G. Conversely, suppose the product of any two right cosets of H in G is again right cosets of H in G. To prove H is a normal subgroup of G, let G belongs to G be any element, then HG and HG inverse are two right cosets of H in G. Thus, HG inverse is also right cosets of H in G. Since E belongs to H, therefore EG inverse belongs to HG inverse. This implies that GG inverse is equal to E. This implies that HG inverse. Thus, the right coset which equals the product of the right cosets HG inverse contain E. But E belongs to H is equal to HE also. Thus E belongs to H is equal to HE and E belongs to HG inverse, again using the fact that any two right cosets of H in G is abelian, identical or disjoint, therefore we must have HG inverse is equal to H. This implies that HG inverse is equal to H for all G belongs to G. This shows that H1 G inverse belongs to HG inverse for all H1 belongs to HG belongs to G. So this implies that H1 G inverse belongs to H for all H1 belongs to H and G belongs to G. So this implies that H inverse of H1 G inverse belongs to H inverse H. So this implies that GH1 G inverse belongs to H for all H1 belongs to H and G belongs to G. Thus GH1 G inverse belongs to H for all H1 belongs to H, G belongs to G. Hence H is a normal in G. Okay. So thank you for listening. We cover the next point in next lecture. Thank you.